Hello, and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about the source-free parallel RLC circuit, where essentially we want to consider this circuit here to the left, where this switch is closed at t is equals to 0 minus, and we've connected this current source IS, and see what happens when we charge this inductor here via a current IL of t, and also see what happens when we charge this capacitor via voltage VC. And now what we want to do is imagine that we take away this current source IS, and essentially this switch here goes to point 2, and now we have this circuit here to the right. And what we want to do is analyze three different things. The first thing we want to analyze is this VC of t, or we could just call this VC, or I can just call this V. And essentially it's the current across my capacitor. Additionally, we want to analyze the capacitor current IC of t and the inductor current IL of t. And so what I'm going to do is I'm going to call this case 1, and I'm going to call this case 2. And before we solve for both these cases, what I'd like to do is define the source-free parallel RC circuit in written form. So now in terms of the definition, we say that a source-free parallel RLC circuit occurs when its DC source is suddenly disconnected and the energy stored in the inductor via a magnetic field and the capacitor via an electric field is released/dissipated to the resistor or the load. And this energy being released or dissipated is in the form of heat. Okay, now for case number 1, we want to consider a situation where the switch is closed and this current source IS has charged up my capacitor here via voltage VC, and it's also charged up my inductor here via current IL of t, where we go ahead and call these our initial conditions. So we say that VC of 0 minus is equated to this VO, or the initial voltage through the capacitor. And what I'm going to do is I'm going to call this equation number 1. So now the second parameter we care about is the current through the capacitor, where I'm going to call this as IC of 0 minus. And we know that the current through a capacitor from a video I've made in the past called What is a Capacitor Clearly Explained, and I'll post that in the top right hand side corner of this video, is going to be my capacitance times the derivative of my voltage VC at 0 minus over dt. And the last parameter we care about is this IL of 0 minus. And again, from a previous video that I did called What is an Inductor Clearly Explained, we know that this current is equated to 1 over L, the integral from negative infinity to 0, V of t dt, and essentially we call this IO. Let me go ahead and call this equation here equation number 2. Something I want to note is that in the case where the switch has been closed for a long period of time, this inductor will actually be a short circuit. So this here will turn into a short circuit. And as you can imagine, the voltage from here A to here B, if we put a multimeter here, will be 0. So VL of 0 minus will be 0. So this is also equals to VC of 0 minus. And then this is also equals to my initial VO. I hope this makes sense, again, because from here to here is essentially VC. Additionally, IC of 0 minus, which is equated to C dVC of 0 over dt, will simply be C times D of 0 over dt, which is equated to 0. And lastly, the current IL of 0 minus, in this case through my inductor, is going to be IS, right? Because if you can imagine, current is going to pick the path of least resistance. So through my capacitor here, it sees RC is equals to infinity because it's a open circuit. And through my resistor, it sees some resistance, right? R is equals to RS. And through my inductor, it basically sees zero resistance. So all my current will flow through here. Again, this is just a special notice in the case where my circuit has reached steady state. As a result, these are my initial conditions. But for this video, we're going to consider a general case where these here are my initial conditions. I hope this makes sense. If you have any questions or concerns, please leave them down in the comment section below and I'll be sure to get back to you. Okay, so for case number 2, we want to consider that we've moved our switch to position number 2 here. And we want to write some equations again to try and solve for this voltage VC of T across my capacitor, or we also just call this V. We also want to solve for this IL of T, and we also want to solve for this IC of T. So that is the goal at hand, where what I'm going to say is that I'm going to write a KCL at this top node here, and I'm going to call this V. So as you can see, using KCL, I can say that there's a current here, IR, there's a current flowing through here, IL, and there's a current flowing through here, IC. So I can write that IR plus IL plus IC must equate to 0. IR is VT over R plus IL is 1 over L integral from negative infinity to T VT dt plus IC is C dVt over dt, and this is equated to 0. Let me go ahead and call this equation 3A, and I'm going to call this equation 3B. If I go ahead and multiply this entire equation by 1 over C d over dt, I can write this term first and say that this is d squared V of T over dt squared plus, if I go and consider this first term here, it becomes 1 over RC dVt over dt plus, for this term here, I get 1 over LC. This derivative cancels out with this integral, and this dt cancels out with this dt. So I'm left with V of T is equated to 0. Again, just to be clear, Vt here is essentially just V. Let me go ahead and call this equation number 4. And we're going to know two things. The first thing is that we want to solve for V of T. So that's the main thing. And the second thing is that equation number 4 is what we call an ordinary differential equation, where the solution for Vt is equated to AE to the ST. I'm not necessarily going to prove this because this was proven in a calculus or differential equations class. But essentially, we can show this by saying that if V of T is equals to AEST, we then know then that, so for example, let V of T equate to AE to the ST. So then dV of T over dt is equated to SAE to the ST. And d squared V of T over dt is equated to S squared AE to the ST. Let's go ahead and sub these functions into equation number 4. I'm going to go ahead and scroll down here just to give myself a little bit more room while keeping equation 4 at the top of the screen. So this here is d squared Vt over dt squared. So we sub it with here. So we get S squared AE to the ST plus 1 over RC. dVt over dt is located here. So it's times SAE to the ST. And this is plus 1 over LC. And simply Vt is located here. So AE st. And we say that this is equated to 0. If I then go ahead and multiply this entire thing by 1 over a e to the st, and note that I can do this because this function a e to the st never reaches 0 as it goes to infinity. So this function here is a e to the st, where again this is t. Okay, if I continue with this, I then get that this is s squared plus 1 over rc times s plus 1 over lc. I hope this makes sense. And this is equated to 0. Let me call this equation number 5. And what we want to note is that this is a quadratic equation, and it's also known as the characteristic equation. So let's go ahead and solve for s here. We say that then s, which is equated to, if we use the quadratic formula, minus b plus or minus square root of b squared minus 4ac over 2a. We simply get minus 1 over rc plus or minus the square root of 1 over rc squared minus 4 times 1 over lc, all over 2 times 1. If we go ahead and simplify this, we get that s is equated to minus 1 over 2rc plus or minus the square root of 1 over rc squared minus 4 over lc. And again, this is all over the square root of 2 squared. And finally, we get that this is minus 1 over 2rc plus or minus the square root of 1 over 2rc squared minus 4 over 2 squared lc. As you can see, this 4 cancels out with this 2 squared. So then this becomes just 1 over lc. Again, let me go ahead and scroll down here. And since this is a video, you can always pause it while you're following along. So now, since this is a plus or minus, I can say then that S1 and S2 are equated to minus alpha, where this here is this alpha, plus or minus the square root of alpha squared minus omega naught squared, where S1 and S2 are what we call the natural frequencies, and these are measured in nappers per second. Alpha, again, which is equated to 1 over 2rc, is what's called the nappers frequencies. And again, it's an NP over seconds. And lastly, omega naught, which is equated to 1 over the square root of LC, is this resonant frequency, or sometimes called the underdamped natural frequency. And it's in radians per second. So essentially, since S1 and S2 are the natural frequencies of my voltage V of t evolving over time, we can rewrite equation number 5 and say that this is S squared plus 2 alpha S plus omega naught squared is equated to 0. I hope this makes sense. With solutions, V1 of t equated to A1 e to the S1t, and V2 of t equated to A2 e to the S2t. Therefore, I can write a complete solution, or the natural response, of this source-free parallel RLC circuit, and say then that V of t is equated to V1 of t plus V2 of t, which is equated to A1 e to the S1t plus A2e to the S2t, where, to be completely clear, let me go ahead and scroll down a little bit. We get that Vt is equated to A1e. S1 is this minus 1 over 2 RC plus square root of 1 over 2 RC squared minus 1 over LC times T plus A2 E to the minus 1 over 2 RC minus square root of 1 over 2 RC squared minus 1 over LC times T. And this here is the solution, or the natural response to this voltage of the source-free parallel RLC circuit. So let me go ahead and box it. And the last thing to note is that in order to find A1 and A2, we need two parameters. And essentially, the two parameters we need are the initial conditions we discussed in case number 1. So we're going to need VO, or the voltage across my capacitor, and dVO of dt, or the change in voltage across my capacitor. Call this V prime of 0. And we say to find A1 and A2. In order to find these two initial conditions, I'm going to take an observation. And we say that we normally know this V0 minus, or just V0. And essentially this here is the voltage across the capacitor, called this V naught. And this was given in equation number 1. Now to find dVO over dt, or V prime of 0, or the change in voltage throughout my capacitor, we need to look at equation 3b. Essentially, this was that KCL equation we wrote down in the beginning of the video. And if you recall, we said that equation 3b says Vt over R plus 1 over L integral from negative infinity to t, V of t dt plus C dV of t over dt is equated to 0. All right, if we take a situation where we say that at t is equated to 0, we have V of 0 over R plus 1 over L integral from negative infinity to 0, V of t dt plus C dV0 over dt is equated to 0, where essentially we want to solve for this value here. So in order to isolate that, I'm going to multiply this entire thing by 1 over C. So what do we get? I'm going to write this term first. So I get dV of 0 over dt is equated to minus VO over RC plus 1 over LC integral from negative infinity to 0 Vt dt. So if you recall, something we had mentioned was that this here is equated to this I naught. So what I'm going to say is, technically speaking, we also use equation number 2, because this here was equation number 2. So then I can equate this. I'm going to plot a minus 1 over C times V0 over R plus I naught. And essentially, just to be explicit, I can write this a couple of different ways. I can say dV of 0 over dt, which is again V prime of 0, is equated to minus 1 over C times the initial voltage across my capacitor, Vc of 0 over R, plus the initial current across my inductor, IL of 0. Or you can say that this is minus V naught plus R times I naught over RC. Again, just to be explicit, V naught in this case is VC of 0, and I naught in this case is IL of 0. I hope this slide makes sense, and I hope that it kind of explains everything that is needed to find the complete solution or the natural response of the voltage in a source-free parallel RLC circuit. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. Now, the last thing we need to do is find those last two parameters we talked about. So the natural response of my current through my capacitor and the natural response of my current through my inductor. So like we talked about, we need to find IC of t and IL of t. We know that the current IC of t through my capacitor is the capacitance times the derivative of VC of t over dt. So then this is equated to C times D times A1 e to the S1t plus A2 e to the S2t over dt. So we can then go ahead and say that IC of t is equated to C times A1 S1 e to the S1t plus A2 S2 e to the S2t. So that concludes that proof. And then for IL of t, we need to look back and visualize equation number 3a. And recall that equation 3a says that IR plus IL plus IC is equated to 0. Where again, we're tasked with finding this IL. So I can say that IL of t, which is equated to capital IL, is equated to minus IR minus IC, or minus IR of t minus IC of t. We know that IR of t is equated to, so this would be minus V of t over R minus C dV of t over dt. So then IL of t is simply equated to minus 1 over R times A1 e to the S1t plus A2 e to the S2t minus C dV of t over dt we just found up here. So we know that this becomes A1 S1 e to the S1t plus A2 S2 e to the S2t. And that completes the second proof. Okay, so in summary, we have found what the voltage waveform in the source-free parallel RLC circuit behaves like. In addition to that, we also found the waveforms of the current through the capacitor and the inductor in the source-free parallel RLC circuit. In the next video, we will draw conclusions such as if the system is overdamped, critically damped, or underdamped, or essentially we'll discuss how these systems behave as time goes from t is equals to 0 to t goes to infinity. If you have any questions or concerns, please leave them down in the comment section below and I'll be sure to get back to you. If you liked the video, please give it a thumbs up and please share the video to your colleagues so they can also obtain the knowledge given in the video. And if you like the content that the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.